centered on consistency of point estimators. Before now, we've been trying to look at the properties of good estimator. Well, number one property of a good estimator is unbiasedness. You know how to, figure or how to obtain that. Another property of an estimator is efficiency. We did that in the last class. If I want to evaluate an estimator, whether biased or unbiased, of course, for the unbiased estimator, I'm going to look at the variance. For the biased estimator, I'm actually going to look at the mean square error. Okay, now that efficiency is not the only property. We talk about unbiasedness property, we talk about efficiency, and what we want to talk about today is consistency, which is another property of a good estimator. I want to say consistency should be after you have investigated efficiency. Because in what we want to do today, we're actually going to be analyzing variance. Does that make sense? Consistency has to do with the variance. Okay, when the variance of an estimator converges to 0, when the sample size is large, of course, what happens? Variance of an estimator converges to 0, automatically the estimator will converge to the parameter. That's what it means. Okay, so like I said, we're focusing on consistency. There's going to be illustration. Consistency is part of the property of good estimator. I'm going to start from here. Please, I need you to be focused. You can still have A in this course. Okay, if you can still have A in this course. Okay, now if y1 up to yn follow Bernoulli, maybe I want to go into population or figure out how many of the eligible citizens approve the work the president is doing. Of course, I'm going to go from one person to the other. The first person is y1. And before going into this research, maybe, because the response is going to be dichotomous, that is, the response is going to be categorical with 2 levels, is either yes or no. If I label yes as 1, those who say yes, the president is doing great, and I label 0 as a non-approver, then I'm actually going to be saying this guy. You see why? Give me 1 second. You see y1 up to y8. Okay, y1 up to y8, 0, 0. The first person said no, the president is not doing great. Another 0 said no. Where you see 1, say yes. That is more or less like tossing a fair coin. Before going to experiment, right? Before going to experiment, or tossing a fair coin, according to the classical approach, the probability of a head showing is 0.5, right? We all know that. But let me tell you this. If we now want to focus on the addition of, like we have all this, and we are interested in the total number of respondents that actually going to say yes. Yes means 1. Okay. If I add 0 to 0, I have 0. I have a 0. If I continue 0 to 1, that will be 1. 1 to 1, 2, 2 to 0, 2, and so on like that. I'm actually going to have the second line. It's like adding the successive 2 together. And what do you think I want to do at the end of the day? I want to find the average. Okay, y1 up to y8, 0, 0. The first person said no, the president is not doing great. Another 0 said no. Where you see 1, say yes. That is more or less like tossing a fair coin. before going to experiment, right? Before going to experiment or tossing a fair coin, according to the classical approach, the probability of a head showing is 0.5, right? We all know that. But let me tell you this. If we now want to focus on the addition of, like we have all this and we are interested in the total number of respondents that actually going to say yes. Yes means one. Okay. If I add 0 to 0, I have 0. I have a 0. If I continue 0 to 1, that will be 1, 1 to 1, 2, 2 to 0, 2, and so on like that. I'm actually going to have the second line. It's like adding the successive two together. And what do you think I want to do at the end of the day? I want to find the average. And I told you the other time, average is the same thing as the estimate of proportion. Average is the summation y over n. If I want to do this summation now, what I'm going to do is, okay, take a look at the 0 here. Okay, 0 divided by 1, 0 divided by 2, 1 divided by 3. You see 1 divided by 3, that would be 0.33. 2 divided by 4, 0.5. Do you know that in the first 7 trials, if you take a look at this guy, we were getting, these values here is actually fluctuating, right? But I want to tell you, on the long run, when you have an infinite numbers of trials, or let me just say, when you have a sufficiently large numbers of trials, we expect the p cap to converge to the true values of p. What is the true values of p? Is 0.5 for a coin. Because before we flip the coin, the if it's a balanced coin, the probability of any of the sides showing up should be 1 over 2, should be 0.5. But what we're trying to tell the world, experimental probability is different from theoretical. Based on the theoretical ground, okay, the theoretical ground actually use expectation, use a classical approach that is going to tell you it's 0.5. But when you conduct an experiment, it's not going to be 0.5, in a small numbers of trials, but we expect that it's actually going to converge to the true value when you have a sufficiently large numbers of trials, and that is consistency. Because what consistency is talking about is when I increase my sample size, the variation that we notice, that we call variance, will actually converge to 0. When the variation converges to 0, we now expect the p cap, which is an estimator here, to converge to the true value of the parameter. So the true value of the parameter here is 0.5. We can also demonstrate this graphically. I need you to see the first graph. Okay, the first graph, what is it talking about? Here, okay, I got 1,000 numbers of trials, okay, but a single sequence. And you can see the convergence. You can see the blue solid line, right? The convergence is not just going to be 0.5 like that. The convergence that we're talking about is actually going to be probability convergence. You remember what we did the other time when we talked about law of large numbers, right? We got a weak law. We're talking about weak law. The weak law is going to tell you the probability of the absolute difference between an estimator and a parameter, less than epsilon. We're trying to say when a convergence is going to take place, it's going to be within the distance. Does that make sense? That's what you're seeing here. But in a situation, this is not looking, there's no way we can get a distribution here. You know why? Because this is just a single sequence. But if I have like 50 sequence, okay, I can look at the distribution. Oh my God, take a look at this guy now. What are you seeing? What are you saying? That's looking like a normal, right? Take a look at that guy. That's exactly what we mean. Of course, we always going to do sampling distribution because our estimator is a random variable. Okay, so if estimator is a random variable, then we can begin to look at the sampling distribution of our estimator. Now, inconsistency, the idea of the large law, the law of large number will be used. I'm going to say that again. For consistency property of an estimator, whether biased or unbiased, we're actually going to make use of the law of large numbers. And don't forget, there are two laws of large numbers. We got a weak law, we got a strong law. We're not talking about absolute convergence here. The absolute convergence is the strong law. We want to focus on the weak law. On the weak law, of course, before, you've done something like this, okay, where we're going to say the probability of the absolute difference. Our estimator here is a sample proportion. Okay, the absolute difference between the sample proportion and the population proportion is less or equal to epsilon. And what you are trying to tell the world, the probability that the sample proportion will converge to the true value of proportion within certain threshold, that probability is going to approach one. That means very, 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 it's with a high probability. Okay, so like I said, we're going to use the idea of law of large number here. Now, I want to put to you that we got two different versions of this law. They are the same. I want to generalize now. For instance, if I want to define, okay, what make an estimator to be consistent. Okay, the other time I walk it through. What make an estimator to be unbiased? Oh, when the expected value of an estimator is equal to the population, the true value of parameter, it is unbiased. And if it is not, then it is biased. Then I've also walked you through what make an estimator to be efficient or to be more efficient than another estimator. We're actually going to compare the variances. Okay, if we're actually focusing on bias estimator, and if we're focusing on a bias estimator, we're actually going to compare the mean square error. Okay, now what make an estimator to be consistent? If I ask you in exam, okay, what make an estimator to be consistent? I expect you to state this. And what are you stating now? You are actually using the idea of the law of large number, the weak law. Now, if you take a look at this guy now, what are we telling the world? You're not going to say, when sample size is sufficiently large, that is what we mean by n tends to infinity, the probability of the absolute difference between the estimator and the parameter less or equal to epsilon equal to 1, what we're trying to talk about, you can see the other time. Take a look at this guy here. What do we say here? Approaches 1, right? Approaches 1. But in case of consistency, we are very, very certain that that is going to happen. The convergence, the estimator will converge within a k distance, within a distance of the population parameter value. That probability is 1. Now, when I change from less or equal to greater than epsilon, of course, that probability will be 0 because we don't want the difference to be greater than a threshold. I need you to read meaning to this. Don't ever learn mathematical statistics or any mathematical related subject, without attaching what I'm going to call analytical mind. I need you to follow this with, you need to be seeing them. What is behind this notation? What is it trying? If I want to tell my grammar now, what I'm trying to tell my grammar is if I have a threshold, and that threshold is an epsilon, right? Then the probability of the difference between an estimator and a parameter, okay, the probability that it will be less than this that I said, that probability will be 1. But the probability that the absolute difference between the estimator and the parameter will be greater than this is 0. You know what I'm trying to say? It is not possible that is going to be greater than that. That's why I say 0, because when the sample size is large, okay, we expect the probability of the difference between the estimator and the parameter to be less than the threshold I set. Does that make sense to you now? Okay. Because of that, the implication now is the implication of these two is that the estimator converges to the true value, and that very convergence is called convergence in probability. That's why you see we put a P. Does that make sense? That's what we call it. That's why we put a P. Okay, because what I'm going to be showing you today is going to be full of notations. I'm not going to deceive you. When I was learning this notation in Africa, it was tough for me. But I actually develop interest in notations when I decided to pay attention to what was behind the scene. A lot of stories are behind the notation. Don't just do mathematics. Don't just do notation, but try to understand what is behind the notations. Okay. So because of that, I'm actually going to I'm going to talk about convergence in probability now. You know, if I have x1 up to x2 and so on like that, the sequence of random variable, and there exists a constant c. Constant c could be a value. Then we say that xn, that xn is a sequence of random variable. That xn converges to c, like it's, you know, maybe it go and run and run and run and run. It was fluctuating and it get to a point, it converge at a particular value c. Okay, then if we, what that means now is this guy here. We're now trying to say the condition of that convergence for xn to c is in probability, and that will only occur for epsilon greater than 0. Of course, the threshold. Epsilon is the threshold that you set. Okay, and that very threshold, if the epsilon equal to 0, what does that mean? Can somebody tell me for extra credit? What does that mean? What kind of convergence is that when epsilon is 0? What kind of convergence? Can somebody tell me? Go ahead. Absolute. Send me a message for extra credit. Okay, for those of you who have earned extra credit, oh, you know, there are some, you know, I forgot to tell you this. I graded only 3 questions. Okay, and there are some students that did 4 questions correct. You know, they did it so nice. You know what I did? I put extra credit plus 4. I've not used that. So for those of you that I wrote plus 4 plus 5, you need to send me a message on how you want to spend it. Does that make sense? Okay. And for those of you who have been earning extra credit in this class, if you want to spend it on this midterm one, send me a message. Does that make sense? And if you want to save it, you can also save it. Okay. For if epsilon, go ahead. This one. Oh, if for epsilon greater than 0. That is what it means. If for epsilon greater than 0. Now, when epsilon equal to 0, just like what he said, that's an absolute convergence. We're not interested in that. Okay. And that was why we're trying to say our epsilon has to be greater than 0. Now, take a look at this. This is the same as what I showed you before. You know, the other time it was between an estimator and a parameter. But right now, it's between xn and c. It's still the same, right? When it is greater than epsilon, that probability will be 0. It's surely going to be zero because it's not going to happen when n tends to infinity. When n tends to infinity, what we expect that will happen is that the difference should be within the epsilon. Less or equal to epsilon. That's going to be equal to 1. So take note of that. Okay. Now, I want to focus. Let me tell you this. I can investigate the consistency of an unbiased estimator. I can also investigate the consistency of a biased estimator. If I want to investigate the consistency of an unbiased estimator, I will be focusing on the variance of an estimator. If I want to investigate the consistency of a biased estimator, I'm going to be focusing on the mean square error. Does that make sense? Okay, now an unbiased estimator theta k for theta is consistent, okay, of theta if as n tends to infinity, what happened to the variance? The variance becomes 0. You know, when the variance of an estimator equal to 0, there's not going to be fluctuation anymore, no variation. Convergence will take place. Does that make sense? That is what this guy is talking about. But you know what? You know, in the law of large number, we use the idea of Chebyshev inequality, right? We're going to use the idea of Chebyshev inequality again. Why are we using the idea of Chebyshev inequality? Because the epsilon, don't forget, what is epsilon? The epsilon will be K standard deviation, right? The number of standard deviation, which is this guy. Take a look at this guy now. You see that guy? Less than that. What is my epsilon now? My epsilon is K standard deviation multiplied by standard deviation of the estimator. Does that make sense? That is what my epsilon, don't forget the epsilon is in terms of K. Okay, now if I want to, and you remember if you want to use a Chebyshev inequality, right? You need to determine your K, right? Don't forget the in the Chebyshev inequality, the probability of the absolute difference between the estimator and the parameter less or equal to epsilon will be greater than 1 minus 1 over K squared, right? Which is this guy here. You see that guy? 1 minus 1 over K squared. Then in that situation, I need to figure out my K. Okay, and what is going to be my K? You know, if this guy here, if this guy here is actually equal to epsilon, okay, what is my K? Then K is going to be equal to that. K will be equal to epsilon over the standard deviation. Does that make sense? Now, by the time you now come here, you're plugging in the expression of the K into here now. You see why you are doing algebra in high school? This is algebraic in nature. I'm going to put that expression now. When I put that expression, okay, you know, you will see that there's going to be square of the standard deviation. What would be a square of the standard deviation? That would be variance, right? Take a look at this guy now. Then I got this guy. When I got this guy now, you know what is going to happen, right? I want somebody to tell me now. I want to award another extra credit. What is the variance of an estimator theta k when sample size is large? Can somebody tell me the expression? Go ahead. What is the variance of an estimator? Like, this is a question. Give me 1 second. What this guy, just this guy here. You see that guy? What is the variance of an estimator theta k? What is the variance? For instance, if I ask you, what is the variance? Oh, go ahead. No, not. I'm not applying answer. I'm just talking about generally speaking. Okay. Now let me refresh your memory. What is the variance of y? Sigma square, right? What is the variance of y bar? Sigma square over n. Send me a message for extra credit. Sigma square over n, which means, don't forget, this is an estimator. And our estimator used to be sample mean, right? Even P cap is a sample mean, right? What is going to happen there? The variance of estimator, where are you going to have the sample size? Denominator. Denominator. When the n is large, what happened? mathematically speaking, what happened to this guy? It's going to be zero. Does that make sense? Because the variance of estimator is a function of the sample size. The variance of estimator is a function of the sample size. So what happened now? What probability do you now get? 1. Which means when n tends to infinity, when the sample size is sufficiently large, what do you expect? When you expect that the parameter and the estimated theta cap will converge to theta within the threshold, and that probability is very close to 1. That's what we're talking about here. Does that make sense? And that will force that to 0, which means the variance is now becoming what? The variance approaches 0. That was what I said. The reason why convergence does not take place is because of variation. The moment the variation tends to 0, what happens? Convergence occur. Does that make sense? Okay. I want to go into other estimators that we've done, the normal some common estimator. But before I go into common estimator, look at what I put. What of in a situation where the theta cap is biased? Okay, now if I come back here and I want to use, instead of k standard deviation, it's going to be k square roots of the mean square error. Does that make sense? Anytime you see k standard deviation, anytime you see standard deviation, that's the square root of variance, which means we're focusing on unbiased estimator. But if you are focusing on a bias estimator where you see k standard deviation, you're actually going to see k square root of the mean square error. Does that make sense? That is exactly what I'm trying to talk about. Okay, here. Okay, in that situation, what we tend to 0? The mean square error. We tend to 0. And when the mean square error tends to 0, what happens? A bias estimator can now be consistent. It is not only unbiased estimator that can be consistent. Even the bias estimator can also be consistent. And the condition for the consistency is when the sample size is sufficiently large for unbiased estimator, the variance of estimator will shrink. While for the bias estimator, the mean square error will shrink. Does that make sense? Okay. So far, so good, right? So far, so good, everyone? Okay. Now, I want to go into some common estimator that we've done before. It's popular in statistical analysis. I got a parameter theta. At times we may be interested in population mean. We may be interested in population proportion. We may be interested in difference of means. We may be interested in difference of proportions. Okay, so if we are interested in that, when sample size is sufficiently large, we said that this guy is going to converge, right? Then all the estimator too, they're also going to converge to the true value of the parameter. Why are they converging? Why are they converging? Because their variances are function of the sample size. And where is the sample size? Denominator. In the denominator. Okay, we'll take a look at the first one. What do you see here? That is a variance. All the variance formula. Why am I using variance? I'm using variance because all these guys are unbiased estimator. When you have a variance in the denominator, when the sample size is large, that will shrink to 0. Any question? Which means, go ahead. Yeah. When the variance converges to 0, the implication of that is that the estimator converges to true value. Yeah. Oh, that's a good question. Like I said, this is another stage. The first stage, one of the property before first started by investigating whether it is biased or not. After that, we move to efficiency. But right now, okay, we've passed the stage of efficiency. We now want to talk about consistency. So if I want to investigate consistency, I may investigate consistency of either bias estimator or unbiased estimator. But when I'm investigating the consistency of unbiased, the focus will be on the variance. If I want to investigate the consistency of a bias, the focus should be on the mean square error. If you take a look at this guy, the common estimator that we have in statistics, they are unbiased. That is why I'm using variance. You can see now variances, and all the variances here that you see, they are function of the sample size. Where is the sample size? Numerator or denominator? Denominator. Then when you have something in a denominator and that thing is becoming large, what happened? The whole expression will converge to zero. And that confirms the consistency of the common point estimators. The takeaway from here is that the common point estimator will be consistent. Okay, give me 1 second. Okay, now, so far so good, right? Okay, now, because that is one of the property of an estimator. A good estimator, okay, is either it is unbiased or biased, even though the ideal one is unbiased, right? Okay, then has to be efficient and has to be consistent. What we're doing today is investigating consistency. Does that make sense? Okay, now I want to go into an example now. You remember the other time on Wednesday where we had two estimators, okay? And I asked you to investigate the efficiency, right? We obtain the variances of the two, right? And obtaining the variances of the two is because of the fact that we realize the estimate of theta cap 1 and theta cap 2 are unbiased. Now, we investigated the variances, but right now we can also investigate their consistency. Okay, now take a look at this. You know, through based on what we did in the last class, we've already obtained, give me 1 second. We've already obtained their variances. You know, we did that in the last class. We already obtained the variances. Now, if I want to investigate consistency, I can investigate consistency from the variance here. You know what I'm going to do? I will set n to infinity. When I send n to infinity in both, in the both, where is n? It's in the denominator, right? The two of them will tend to zero. Do you see that? Because each of the variance tend to zero when n is large, then I'm going to say theta cap 1 and theta cap 2, they are both consistent estimator. But imagine if theta cap 1 and theta cap 2 are biased estimator, then what I'm going to investigate will be mean square error. And don't forget, mean square error equal to variance plus the square of bias. Does that make sense? Okay, any question on that? I'm done investigating consistency. But let me tell you this. Imagine in exam, I ask you to investigate the consistency of, maybe I gave you this. Maybe I gave you these two estimator, and I ask you to investigate the consistency. Oh my God. You're going to, for us, you do what we do on Wednesday, where you're going to derive the variance. You start with the expectation, you see whether they are unbiased or not. Because if they are biased, you need to compute the mean square error. Now, after having, we did a lot before having these two guys in place. I remember what we did on Wednesday. We were looking at the relative efficiency, right? Where we look at the ratio of the variance, right? We're trying to investigate the one who is more efficient, but we're not interested in that today. What we're interested in today is we want to investigate whether each of them is consistent or not. Does that make sense? Okay, now when we are investigating, what we're doing is we are finding the limits. We are finding the limits of the variance as n tends to infinity. That is what we're doing. As n tends to infinity. When n tends to infinity, because the n is the denominator, the whole expression is going to convert to 0. And when that happens, then the conclusion is that it is consistent. Now, what if I ask you this? How do we justify the convergence of this? How do we justify the convergence of the difference of sample mean to that? If I want to justify that, what am I going to do? I only need to investigate their variances. What is the variance? That is part of the common estimator. Okay. Give me 1 second. I'm going to clean this now so that you're going to see this guy here. What am I going to do? I'm going to set the sample sizes to 0. I mean to infinity. And that will be consistent. That's what I mean. Now, I want to go into another theorem now. There's a theorem in statistics that we call Silovsky theorem. For instance, suppose theta cap n converges in probability to theta. Maybe we have two different estimators. They converge. The two of them convert to different things. Okay? Theta cap 1, of course, you now know if you are talking about convergence in probability, right? The convergence in probability, okay? Suppose that theta cap n converges in probability to theta, and another theta cap converges in probability to that. Okay, let me tell you this. If we're producing two different things in this company A, this company B, and what they produce varies in terms of number. What they produce varies in terms of number. But you know what? Every company has a target value, right? Like the total production they are anticipating. That would be a true value, right? But at times, depending on the ability of workers, equipment, and so on like that, there's possibility they may not meet their target. Does that make sense? Now, if the value of what they produce in this company converges to a value, and the values of what they produce, another item converges to a value, I'm now interested in adding, okay? The addition of these two estimators now will also converge to the totality of the parameter. That's what we're saying. Okay, now that is for addition, that work for multiplication, and that work for division as well. You know, if we're talking about algebra now, okay, and you got two estimators, so that you add them, multiply them, divide them. Okay, that's exactly what we're trying to say. Now, I'm going to give you one example. Take a look at G. So if G dot is a real value function that is continuous at theta, then G of the estimator converges in probability. We can have a situation where a function converges to another function provided a random variable within this function converges to a random variable within. It's just like this is United States. This is Canada. Okay, there's somebody here, is a friend with somebody here. Before you know, at the end of the day, if a lot of people here now is a friend with a lot of people here now, what happened between United States and Canada? They converge, like, oh, we are now friends together. That's what it means. Okay, so that is what we mean here. Now let's take a look at an example. Exponential of an estimator converges in probability to exponential of the real value. Whatever mathematics I want to conduct, whether exponential or sine or log or whatever, okay, if I do that on the estimator, okay, then that will converge in probability to the true value. That's exactly what I'm trying to say here. Do you know that that law here, that law in A enable us enable, this, because plus or minus also go, you see, if that doesn't hold, this is not going to hold, because you know why? Y bar 1 converges to mu 1, y bar 2 converges to mu 2, then the difference between them will converges to mu 1 minus mu 2. That's what we mean. Without that very law in place, it will be impossible for these. And that's exactly what we mean here. Take a look at that. Do you know, which means this is conditional. Before the convergence of this is going to take place, that is if and only if this has taken place. Any question? Okay. I want us to come here. I'm not going to finish this material today. I'm going to start with this same material on Monday, because I really want you to get, the information. Okay. I needed to get the information. Oh, okay. Okay. Now, let's talk about variance. Suppose y1 up to yn represent a random variable such that expected value of y equal to mu, expected value of y square equal to mu 2. The mu 2 that you are seeing is what we call the second moment. The expected value of y4 equal to mu 4, okay, like a fourth moment. Then they are all finite. Finite means, you can get a value for them. Okay, they are determinate. That is what I mean. They are determinate. Now, you remember this guy, right? You remember that guy, right? As a sample variance, right? Now, that we showed the other time that is an unbiased estimator. You know that? We showed that the expected value of this guy is going to be equal to sigma squared, right? It's an unbiased estimator. Now, we now said it's a consistent estimator of sigma squared. How am I going to know it's a consistent estimator of sigma squared? Okay, if I really want to know, okay, then this is an estimator, and then I need the variance of this estimator. Because when I go into population, right, if 1,000 researchers should go into population, they're going to compute 1,000 variance value, right? Therefore, variance become an estimator. If I want to know whether this sample variance is consistent, then I need the variance of the variances. They're going to be like, if I have 1,000 investigator, I will have 1,000 value for variance. I find the variance of that. Then I will now investigate. What am I going to investigate? I'm investigating the variance as n tend to infinity. I expect the variance to tend to 0. Okay. And that is what the consistency is talking about. I think what I'm going to do, I'm going to stop here for today. And I'm going to start from here. We're going to continue from this material on Monday. Is there any question about what we've done today? Is there any question? Like I said, on Monday, I'm going to release makeup, and that very makeup will be left open until Friday, 11:59 p.m. You can only spend 15 minutes on the exam, because the moment you click on start, you can start at any time between Monday and Friday, because the moment you click on that, your time is going to be running out. It is not compulsory. That makeup is for students who want to improve on their grade. And if your score is going to be lower than, God forbid, if it is lower than this score, then this score is going to stay the same. Does that make sense? You got nothing to lose, but something to gain. Go ahead. Okay, this is what happened. Because to be fair to those who actually who actually score very high in the first test, what I'm doing is the weight of that makeup will be 70%. So whatever you score in the makeup is going to be 70%. And whatever you score here will be 30%. So what I'm going to do, I will multiply 30% by your score here, 70% by the makeup, provided you score higher in the makeup than what you have now. Does that make sense? Anyway, that is going to be a personal decision. So, you know, I like that. So, you can work it out. Like, okay, do I need to go for this? That's what I mean. But what if you score 100? If you score 100, that will be multiplied by 70%. You can work it out. Before you go for it, assume some score. If I score 100, which is possible because it's going to be multiple choice. If I score 100, 100, if I score 100, it means I got 70. Yeah. Then I will now come here to the original score. I will multiply whatever I score here by 30%. Then I will add it to the 70. I think there should be an improvement. Does that make sense? Provided somebody score very close to 100 in the makeup. But you know what I'm going to do? This is a deal. I will make a video on Sunday on the solution of this midterm, and I will publish it on YouTube. On Sunday, before you go for the makeup for Monday, four of us watch the video about the solution. I'm going to explain this. Does that make sense? Okay. Make sure you stay safe and have a lovely weekend. Bye for now, everyone. Yeah, you can keep it. Yeah, it's yours. Yep, keep it. It's yours.